Today I'll present two experiments in which we investigate the effect of channel selection in different cochlear implant processing strategies on speech intelligibility. Cochlear implants electrically stimulate the auditory nerve, resulting in the perception of sound. To encode acoustic information into the pattern of electrical stimulation pulses used by the implant, cochlear implants bandpass filter the incoming sound signal into a set of discrete frequency bands, each of which provides information transmitted by one electrode. The most commonly used processing strategies use the envelope within each frequency band to modulate the amplitude of a pulse train applied to each electrode. This is demonstrated visually through comparison of the speech spectrogram on the bottom left and two electrodograms, or representations of cochlear implant stimuli across electrodes, in the middle and on the right. The two most common envelope-based cochlear implant processing strategies stimulate either all electrodes, as in the case of continuous interleave sampling, or CIS, shown in the middle, or use channel selection to select a subset of electrodes within each processing cycle, as in the case of the Advanced Combination Encoder, or ACE, shown on the right. Previous comparisons of CIS and ACE either found that ACE improved speech perception over CIS or found no difference in performance with the two strategies. These differences may reflect the variability in speech performance often observed across CI listeners, or the use of different maskers and target-to-masker ratios employed across these studies. For instance, studies that found improvements with ACE only examined speech intelligibility at positive target-to-masker ratios, where ACE is likely to discard masker-dominated stimulation pulses. Considering a target speech signal, highlighted in purple, and three different types of maskers, either speech-shaped noise, a four-talker babble, or a competing talker, the CI stimulation patterns resulting from these target and masker mixtures would differ across CIS and ACE due to channel selection employed by ACE. In a positive target-to-masker ratio, such as the 10 dB shown here, ACE is likely to select target-dominated stimulation pulses, thus enhancing the target signal. If instead the target-to-masker ratio was negative, such as in the case of the negative 3 dB target-to-masker ratio shown here, ACE will likely select masker-dominated pulses, as shown in this four-talker babble scenario. Considering that real-world listening conditions often contain non-stationary maskers, such as competing talkers in which the instantaneous target-to-masker ratio fluctuates, this study investigates the effect of channel selection and the possible interaction between strategy and masker type on speech intelligibility. To isolate the effects of channel selection, this study tests typically hearing listeners using a vocoder that simulates the electrical current spread that occurs in cochlear implants. Two studies are run. In the first experiment, we characterize psychometric functions across maskers for two different settings for this electrical current spread, -8 and -16 decibels per octave. We then compare the measurement precision across these two spread conditions across maskers, and select a spread condition that results in equivalent measurement precision across maskers. We then employ that spread condition in experiment 2 to measure both speech reception thresholds and the percent of words recalled at two stationary target-to-masker ratios across the three maskers and the two strategies. All speech intelligibility outcomes are measured using the UK matrix sentence test, and statistical analysis is performed using linear mixed effects modeling. After collecting the percent of words recalled across a range of target-to-masker ratios for each combination of spread amount and masker type, psychometric functions were fit to individual participant data. The statistical analysis indicated that the mean psychometric function slopes differed across the maskers in the -16 dB per octave condition, but not in the more difficult -8 dB per octave condition, indicating equivalent measurement precision using the -8 dB octave spread. Experiment 2 was then run using this -8 dB per octave spread. When examining SRT outcomes in experiment 2, there was a clear effect of masker on SRT outcomes, as expected, but no effect of strategy or strategy-masker interaction was observed. Both strategies demonstrated similar trends in speech intelligibility across maskers, with worse performance in the four-talker babble and best performance in speech-shaped noise. In general, the SRTs were positive, with only a few subjects obtaining negative or near zero SRTs in the speech-shaped noise condition. When examining the percent of words recalled at either -3 dB or +3 dB target-to-masker ratios, there again was a significant effect of masker, but no effect of strategy and no strategy-masker interaction. Overall, these results indicate that there is no effect of channel selection on speech intelligibility for the conditions and target-to-masker ratios examined here. Specifically, there is no effective strategy and no interaction between strategy and masker under the conditions tested. While it is likely that ACE selects masker-dominated pulses at negative target-to-masker ratios, the conditions employed here were not sensitive to the aggregate effect of that channel selection on speech intelligibility. To better reflect this potential mechanism of channel selection, future investigations should employ more challenging target-to-masker ratios with consideration for real-world listening conditions. Here are the references mentioned in this work. And thank you for listening. I look forward to your questions.